Hi, g'day. Today we're going to be looking at our first video in kinematics. And what kinematics is, it's the study of stuff that moves. So any sort of movement, and in particular in specialist maths what we're talking about is things that move along a straight line. So we restrict it to, it's called rectilinear motion, and it's motion along a line. So it's not two-dimensional, it's not three-dimensional, it's just one-dimensional movement. So I've got some particle or ball or something like that, and all it's able to do is to move this way or that sort of thing. So it just moves left and right or up and down or in and out, just in one line sort of motion. And so that's what we're talking about. And I'm just going to spend this video just sort of like defining a bunch of different things, and we'll get into some examples further down the track. So if we do have this line, and what we can have is we can have its origin, and that's sort of where we measure everything from. And then let's say we have 1, 2, 3 different units from the origin, and we'll have -1, -2, etc. from the origin. And we'll define where the position of the ball, we'll call that x. So let's just say x of t, its position at time t, we'll just write that as position at time t. Okay, and so in other words, if the ball was here, that would mean x is equal to -2. And if the ball was here, that means x is equal to 3. So it's just its position, and its position is always relative to something, and in this case it's relative to the origin. So it's 3 from the origin, this one is -2. And just notice the direction, you've got a positive direction going that way and a negative direction that going away. So these are vector quantities, they have direction. Okay, so that's the sort of the first thing, position is important, so x is its position. Secondly, we have what we call displacement. And displacement is how far has the particle moved from its starting point. Okay, so I might go to I'll just do it here. So displacement says that if that's 0, -1, -2, that sort of thing. If it starts at 0 and goes this way and then this way and finishes here, then we say it has a displacement of 2. Okay, so it's ended up at 2, it's ended up +2 from where it started, +2. Okay, so that sort of thing. If it starts from 1, starts from here, and I'll just be careful, in fact I'll just get rid of that last thing. Let's say it starts from 1 and goes in that direction and then this direction and then back this direction and finishes at -2. What would the displacement be there? Well, it started at 1, it ended up at -2, and so its displacement is -3. It's moved, it's ended up, we don't care whether it's gone left and right, started and stopped or anything. Displacement, just how far it started from its starting point. So it's moved -3, so that would be its displacement. So that's important to understand. The next thing to understand is distance, and that's just how far has the particle travelled. Going to abbreviate it a little bit, sorry. How far has the particle travelled in total? Okay, so that same line there, got 0 in there, 1, 2, 3, 4, that sort of thing. If it starts here, goes that direction and then there and finishes here, the distance is how far has it travelled in total. So it's travelled 1 here, 1, 2, 3 to here, 4, 5, 6, 7. It's travelled 7 units. So, if you were a little ant or something and you're following this path, how far have you travelled? 1, 2, 3, 4, 5, 6, 7 units. And so that's the difference between those. So it's really important to understand the difference between those. Let's have a look. Let's just keep following this diagram. That's the distance travelled. How about the displacement? Well, the displacement in this case, displacement will be equal to, well, it's moved 1, 2, 3, so it's the same as the last one, -3, it's moved 3 to the left. And what would its position be? Well, its position at time 0, where does it start? It starts at 1, and its position at the end is equal to -2. Its position there, -2. So you need to understand the difference between position, displacement and distance. It's important, otherwise you might get tripped up on some of those. Okay, so there's a couple of definitions. Alright, so onto something else now. So just to be able to use those, what we're going to talk about is velocity. And what velocity is equal to the change in position over the change in time. Okay, so just in case you don't know this notation, the triangle means the change. So the change in x over the change in time. Okay, so that's our velocity. We get average velocity if those are not very accurate measurements. Okay, so in other words, if you have x2, so a final position minus initial position x1 over t2 minus t1, you can see this is the change in position, x2 minus x1, and this is the change in time down the bottom. So that's equal to delta x over delta t. That's average velocity. What we're probably much more interested in is instantaneous velocity, and this is what happens when our delta x and delta t become very, very small. In other words, we're looking at very, very, very small chunks, and so we're getting instantaneous velocity. And basically what it is as delta t approaches 0, then we get something much more accurate. What that is dx dt. In other words, the calculus derivative, dx dt. And that's how we calculate that. If we know some function x is a function of time, then all we need to do to find the velocity, that's equal to dx dt. We just need to take the derivative of x to find the velocity function. And that's very, very important. So that's velocity. Let's have a look at the next step in the chain, and that is acceleration. So acceleration. What is acceleration? Acceleration is the change in velocity over a change in time. In other words, it's how fast is the velocity changing. If you get a very high acceleration, your velocity is changing very, very quickly. So delta v, the change in velocity over the change in time. So an average acceleration will be equal to some final velocity minus an initial velocity, in other words the change in velocity, over the final time minus, sorry about that, should have just been t2, not sure what I'm doing, over t2 minus t1. Okay, so the change in time. That's your average acceleration. Again though, what we're really interested in is instantaneous acceleration. And that's the change in volume over the change in time. As the change in time approaches 0, we get the derivative. So that's dv dt, the calculus derivative of velocity. So if you have acceleration written as a function of time, then you can take the derivative of that. dv dt is equal to a, and so we've got that. So I'll do start a new screen, but I'll just describe the relationship between all these three things I've just spoken about. So firstly, we've got our position. If you take the derivative of that, d dt, you get to the velocity function. If you take the derivative of that, space d dt, you get the acceleration function. Okay, so dx dt, I'll just write it here, so that's like dx dt, which is equal to that. If you take the derivative again, that's d squared x on dt squared, you get the acceleration function there. So that's really important to understand this. If we go back in the other direction, we've got the acceleration function. How do we get to velocity? Well, it's the opposite of the derivative. We'll take the integral of at dt, and that gets us to the velocity function. Velocity function, how do we get back to the position function? That'll be the integral of vt. We take the anti-differential to get back to x of t. And this is a really important relationship to understand, how to get between position, velocity and acceleration. That's super important. I'm just going to cover off on a few other little things before I'll sort of do some examples. Just a few, some housekeeping. Velocity, because it's change in position over change in time, it gets measured in things like meters per second or kilometers per hour, things like that. But we need to know how to change between meters per second and kilometers per hour. If you remember, let's have a look at an example. So 5 meters per second, if you're going to change that to kilometers per hour, how many meters are there in a kilometer? It's 1,000, so you'd need to divide by 1,000. So it'd be 5. So you'd need to times divide by 1,000. And seconds, you'd need to get hours into seconds, you'd need to times by 60 and then times by 60. Okay, so you get something like that. So what that is 5 times 3600 of 1,000, which is 5 times 3.6. In other words, if you're going meters per second into kilometers per hour, you multiply it by 3.6. Okay. The other way, if you're changing kilometers per hour into meters per second, you do the opposite. You divide by 3.6. Okay, so that's the important information we need to know. Times by 3.6, divide by 3.6. Meters per second is a smaller, it's a bigger unit than kilometers per hour, but if you'll see it, it's smaller numbers. So 5 meters per second is equal to times 3.6, so 18 plus 3, so that's 21 kilometers per hour. So if you've noticed that your meters per second has gone up after, it's higher than the kilometers per hour, you've done it wrong. So just check that which one's bigger than the other. Just finally, I just haven't spoken about this, but what speed is. Now speed is a scalar, whereas velocity is a vector. Okay, so velocity has magnitude and also has a direction. Okay, whereas a speed only has magnitude, it has no direction. Okay, only that. So if you have the velocity is equal to 2 meters per second north gives you your direction, 2 meters per second gives you the magnitude of the velocity, whereas the speed is equal to simply the magnitude of the velocity, which is just 2 meters per second, and we don't know what direction it's going in. So that would be the speed for that. Okay, so speed is simply the magnitude. We don't worry about it's north, south, east, west, plus, minus, anything like that. We don't know. So again, if the volume is equal to velocity is equal to -3 kilometers per hour, the speed will be equal to 3 kilometers per hour. It's just the magnitude of it. We don't worry whether it's plus or minus. It's just the modulus of that, if you like. Okay, that's all it is. Just one more thing I'll talk about. Just x of t, remember, is position. The velocity t is equal to dx on dt, and just in case you see it, it can be also rewritten as this, which is the first derivative of x. So that's important to understand. Acceleration is the second derivative of position, and so we write that as x double dot t. And so that's important to understand as well, just so that if you see this notation, you know it's the second derivative, this is the first derivative. And in the next video I'll do some examples. Thank you.